All
All
right.
right, perfect. Well, after a few technical difficulties, I'm glad that we're up and running. Hopefully you're able to see my PowerPoint. Can I get confirmation on that?
Yes, you look good.
Excellent, perfect. Well, good morning, everybody. Afternoon for me here in North Dakota. My name is Brady Goettl. I'm the Extension Soil Health Research Technician and PhD candidate here at North Dakota State University in the School of Natural Resource Sciences. Sorry I couldn't be with you all there today in San Diego. With finishing up the PhD, I have a lot of other irons in the fire, but now that the weather has come in, it's currently 15 below here in Fargo. I really wish I was with all of you guys there right now. Regardless of how bad the weather here is currently in North Dakota, fortunately, we have very good conditions for growing a lot of crops up here in the state. And I've had the opportunity to work with some of the folks there with AMBA and some of the other brewing and malting industries over the last few years, working with nitrogen recommendations on specifically two-row malting barley. And that's really let me dig into creating nutrient recommendations, not only to improve barley, but also to improve profitability, quality, and environmental stewardship of other crops as it relates to nitrogen management. So over the next 20-ish minutes, there's three main things I want to cover. So first of all, why does soil fertility matter to us from an agronomic standpoint and also from an environmental standpoint? And then how do we at NDSU approach developing recommendations? What factors do we take into consideration? And then finally, once we do have that recommendation developed, how are we going to implement that on farms, make farmers understand why it works and potentially why some of our recommendations are a little bit different than they have been in the past or are in other states? So to set the stage a little bit, I just want to briefly go over some of the plant essential nutrients, the elements that we are going to be applying in our fertilizer. So in total, obviously there's 17 plant essential nutrients, but of those, about 14 are provided chemically by the soil. So the other three, carbon, hydrogen, and oxygen, we're not going to be applying those as a nutrient on our field. But the other 14, we are going to be applying in some settings, and generally supplementation of these is going to be required to meet production needs. Now, throughout this presentation, I'm going to address some partial truths that are kind of floating around in mainstream today about nutrient management and reducing rates. And one of them is this idea that we are going to be required to supplement some of those nutrients. In a very healthy native system, we're able to cycle a lot of the nutrients around. So we're not required, obviously, to apply those. And there's within certain groups, the idea that if we improve soil health so much that we're no longer going to need to apply some of the nutrients. Now, it is absolutely true in some of the research I've done that improved soil health systems do increase nutrient cycling and do reduce our dependence on outside sources. But when you think about your high school chemistry class and the law of the conservation of matter, if we're removing grain or stover or anything from those fields, that's taking nutrients with it, and we're going to be required to supplement those back into the field on one way or another. And generally, in most production systems, it's your nitrogen, phosphorus, potassium, and sulfur that are going to be in the most demand for supplementation. So why do we need to apply all of these nutrients? Like if we had, enough calcium and magnesium in our soil, do we require as much nitrogen? And this goes way back to Justus von Liebig and a lot of early research he did on, at the time, soil chemistry, and recognized that yield is proportional to the amount of the most limiting nutrient, whatever that may be. And this is especially important now as I've been involved in a lot of question and answers about reducing our dependence on nitrogen. Other countries, there's several in the European Union that have implemented mandates on we are going to reduce amount of nitrogen applied to fields by 50% by X date. Now, the issue with looking at it that way, yes, it's good to reduce our dependence on applied fertilizers, but we also have to recognize where that reduction is coming from. If the current benchmark is the rate of nitrogen that's going to be required to meet our maximum yield potential, and we reduce that by 50%, that is now going to become our most limiting nutrient, and we're never going to be able to reach our yield potential again, regardless of the other factors we're applying. And now since that yield potential is limited, now we could start seeing loss of other nutrients that are in excess on those fields. So recognizing that nutrient management really is a balancing act, and that we need to dial in our nutrient recommendations, not only to meet the needs of farmers, but also those that are going to meet the needs of environment and regulatory groups as well. So when I start talking about applying too much or too little nutrient, a lot of this can be visualized looking at this curve. So it's called the deficiency or sufficiency curve. And you can look at the y-axis, plant performance. We can also consider that as like yield or productivity. And the x-axis, where it says tissue nutrient concentration, that you could also look at from the term of nutrient available in the soil or applied nutrient. And what this is essentially telling us is when you have a low nutrient concentration in the tissue or in the soil, you're going to have decreased plant performance. Now, as we apply more of that nutrient, as we'd expect, we're going to reach higher potential plant productivity. The issue is, and a lot of the environmental issues come when we start getting on the lower end of this curve, where we're excessive or toxic. That opens the door, one, for lower plant productivity from toxicity. Essentially, it's getting poisoned by too much of a particular nutrient. In addition to looking at it from a barley standpoint, if we over-apply nitrogen, we're going to start having plant lodging. So our harvestable yield is going to go down. And that opens the door for additional nutrient loss from excess application. So all the work that's done, across the country and world on nutrient recommendations is really trying to hit this sufficiency range. Now, and I'll talk about in the future of this presentation, the way you write those nutrient recommendations, you're interested in where you hit this sufficiency curve. So in some of the older recommendations, you're trying to maximize yield. So you want to be at the top of this curve. In some of the work that we're doing here that I'll talk about, we're trying to be the most economic to make nutrient use efficiency the highest as possible. So we'll actually be a little bit lower on this curve. And I'll explain why that works here in a few minutes. So when we start developing our ideal nutrient rates, it's really a balancing act of maximizing yield and optimizing quality, while at the same time balancing nutrient loss and excess application. If we want maximum yield, we are going to have to apply more nutrient than that's necessary for the environment to completely handle. So you can't have the best of both worlds, and the best that we can do when developing our nutrient recommendations is to balance both of those so that we're meeting the needs of all the different groups per se that are involved with these recommendations. So for the rest of this PowerPoint, I'm going to focus specifically on nitrogen as it relates to malting barley. So when we visualize that sufficiency curve that we went through a few slides ago and apply that to barley, what does it look like from an agronomic standpoint? So if you're on the deficient side of that curve, under-fertilized, it's going to lead obviously to depressed yields. That plant is not going to reach productivity. From a quality standpoint, we're going to have a high rate of thin kernels, so kernels that aren't going to meet those malting requirements. And then it also opens the door to low plant health, which could lead to different disease issues. It's just like our bodies, if we don't give it the vitamins and nutrients that we need, it opens the door for a lot of other health issues. And the exact same thing is true with plants. Jumping all the way to the other side of the spectrum, over-fertilization, that's going to lead to excessive grain protein content. Again, over-applying that nitrogen, you're no longer going to meet those malting requirements. As I talked about before, the grain lodging, so we're no longer going to be able to harvest some of that grain from the over-fertilization and having it fall over. And then again, if we over-fertilize, more nitrogen is going to be available to leaching, and it's just going to cost more money. So in this balancing act, what are we shooting for? What did we shoot for here at NDSU when we developed our new recommendations? And that optimal rate was something that really had the ideal grain quality for malting. That was one of our most important aspects. And second of all is to maximize profit for the farmer. Now you notice I don't talk about maximizing yield here because there's a disconnect between yield and profitability when it relates to nitrogen. So our main goal was to make the most profit, and that also fortunately, maximum profit equals maximum use efficiency for that nitrogen. So a little bit of background on the study that we did. So we created a new data set for these recommendations. by establishing replicated, regionally applicable research plots. So these 2 points become especially important in nutrient management research, that we need the research to be replicated, obviously, so we have good scientific data. But each region has its own specific way it'll cycle nutrients. The climatic factors have an impact on the way those nutrients cycle. So by having research regionally in the main production areas, we're able to replicate what's being faced on farm. So I'm going to focus on a smaller sub-data set of this, where we had 2 experimental sites over 2 different years in East Central North Dakota. This is the research that I've been working on for both my master's and my PhD project, where we applied 5 different nitrogen rates on all of these sites, ranging from 0 up to 160 pounds of nitrogen per acre. And as we go on, I'll talk a little bit about some of the different ways that we're measuring fertilizer value. And then lastly, this study is looking at 2 different multi-barley cultivars, Synergy and Genesis, working with some of the folks here in North Dakota. These were the ones that they recommended that are being most used currently and in most demand. So after 2 years of experiments, we were able to collect a lot of really good yield and quality data. And a lot of it is kind of what we expected. There's been a lot of research done over many, many years on the nitrogen impact on crops. So as we would expect, as our N rate increased, we also saw an increase in grain yield. Now, what we have to note here is grain yield in this barley only increased up until a certain point, where you start seeing, a kind of a plateau happening here. So that's that idea of when we start reaching the top end of that curve, we're no longer gaining as much yield as we did in the lower part of that curve. And that comes back to that use efficiency idea. Start looking at some of the grain quality factors, grain protein content. Again, we saw an increase in that kernel protein as the N rate increased. And one thing to keep in mind here is at the point where the yield started to plateau off at around 80 pounds of nitrogen per acre, grain protein continued to increase, and we didn't hit that plateau until later. And in some of the graphs I'll show you, it'll actually continue in a linear progression of grain protein content increasing. So that means if we do over fertilize, not only are we going to be losing money on that, but we're going to get farther away from those optimum quality requirements. Kernel plump and test weight, also 2 important quality factors. We didn't necessarily see any statistical difference from the nitrogen rate on those 2 factors. And a lot of that relates back to, we're only looking at fertilizer rates in this particular table, but there was fertilizer available in the soil from previous crops and the spring nitrate tests. So for the rest of this presentation, when I talk about nitrogen rate, I'm going to just say it as total known available nitrogen. So that would be the sum of all nitrogen sources that plant has access to, not only fertilizer, but also the soil nitrate that was available at planting, in addition to crop credit. So that crop credit would be perhaps a soybean or a dry bean planted previously to this barley crop, which would release around 40 pounds of nitrogen throughout the growing season that would be available. So from this data set, let's actually create the recommendation. Now we know how the N and the yield interact with each other, but how do we maximize this to try to replicate it on farms, which exactly is what the recommendation is. So the few different approaches we can use. The most traditional is the yield goal approach. And then in recent years, this relative standard yield approach has been developed originally for corn, and now it's been slowly expanded to other grains, first wheat, and now here in North Dakota, we're the first ones to expand it to malting barley as well. And then lastly, the economic optimum nitrogen rate, which is combined with some of the other approaches to produce a more applicable and financially stable recommendation. So starting with the yield goal approach, this was one of the most popular approaches and still is used in a lot of states for over the last century. And what it did was attempted to relate yield directly to nitrogen availability. So essentially, they could create an equation saying, if you want 50 bushels of grain, it would take this many pounds to create that bushel. So you'd simply multiply whatever your goal is by that N factor, and that's going to give you how much nitrogen you need to apply. Now, logically, this makes sense, but also that it kind of starts to break down as we start looking at some of the actual data. So if we were to take, this is data from that experiment I talked about earlier, and we wanted to create a yield goal recommendation from it, we would simply plot grain yield on the y-axis against that total known available nitrogen at the bottom and fit it with a curve. So what this shows us is as we apply more nitrogen or more nitrogen is available, the yield is going to increase up until a certain point where we're not going to see any difference anymore. So to create a yield goal from this, we would say, at 100 pounds of, or if your yield was 60 bushels per acre, you need to apply, 115-ish pounds. And that would linearly increase all the way up until this point, at which you would say, you're not going to have a yield goal over this amount. Just that would be the maximum amount of nitrogen you need to apply. Now, this makes sense, but like I said, it starts to break down when you realize that the relationship in that last graph really was not very good. It took many different regions, different weather patterns into consideration, but not necessarily with the same amount of weight. On a drier year, you're going to have a lower yield. But we're trying to compare that now to the high yield years, which makes it difficult to create solid recommendations from it. You also then have to predict the yield at the time of fertilization. So pulling into your field in the spring, if I had a crystal ball that would tell me what my yield was going to be at the end, it would make farming for me a lot easier, but we're not necessarily able to do that. So we just have to assume what we think our yield goal is going to be, not taking into consideration what changes in weather and such that we may have. And then, like I talked about earlier, it ignored that field-to-field variation of N efficiency and N cycling, which then really relates back to different yield potentials. But why is it done? It's a very easy way. I could, collect this data and have a yield goal recommendation put out in the matter of, minutes. And also it's logical to expect that fertilizer and yield are related. My advisor told me this quote a while back, and I always thought it was fairly humorous. Whenever I said something was logical, he would say, well, logic is the systematic method of coming to the wrong conclusion with confidence. And that, I think, applies really well to this yield goal approach for nitrogen recommendations. So what did we do here at NDSU is focus on the relative or the standard yield. And essentially, we take that same data that we had talked about previously, but we standardize the yield within each environment, meaning whatever that particular plot or field maximum yield was, whether it be 100 bushels or 50 bushels, we say that yield is the maximum. It is equal to 1. And all the other yields at that site are divided by that maximum yield, which gives us a percentage. And then we can combine all of those sites together, and then they're on a relative or can be compared to each other because it's not taking all of those extra climatic considerations into factor. And again, combining that data, they're all equally representative regardless of what that actual yield was. So bring up in your mind again what that yield goal curve looked like, kind of the spattering of dots when we did not go through that relative yield calculation. Now that same data, when we standardize it, actually forms a very nice curve. And that's good for us because now we recognize that this is a stronger relationship. We're being able to make better recommendations off of it. And also what is interesting is regardless of the environmental factors, the nitrogen use efficiency of this particular crop is similar. So if we were to stop here and base our recommendation off of it, we could say that maximum yield, the top of this curve, is going to be around 186 pounds of total known available nitrogen per acre. So again, that includes fertilizer nitrogen and the other sources that were in the soil or become available throughout the growing season. If we look at then the grain protein content at that same nitrogen level, on average, it would be around 12.8%, which is approaching that cutoff of 13 that's been set by a lot of groups, but is still on average going to be below that. Now, the question always comes up, and I keep talking about how this approach takes some of the variability out. We can then see that plotted on that curve, all of the yields are somewhat similar regardless of what the actual yield is. Well, how is that so? So let's first look at some low yield environments. Now, this could be a field that's too droughty, maybe a little bit too wet, depending on the weather. It may have a sandy or too clay texture. And what that leads to is a lower nitrogen use efficiency on that particular field. So that could come from less N mineralization. So some of that organic matter breaking down from previous crops and becoming available to the current plant, and also lead to potential denitrification. So if that field is too wet, some of that nitrogen can be changed by the biology in the soil and actually be lost to the atmosphere. So that lower nitrogen use efficiency means we're going to have to apply more nitrogen per unit of potential yield. Now, on the other side of that is we have a high yield environment. So moisture is ideal. We have a good soil texture, just an overall good year that farmers shoot for and like to talk about. That field is going to have a higher nitrogen use efficiency. So per unit of N available, we're going to be able to produce more potential yield. And again, that could be related to greater N mineralization. But what I want you all to take away from this is, regardless of whether we're in a low yield environment or a high yield environment, the rate to produce that maximum potential yield is similar. That goes back to that last graph that I showed you, where regardless of environment, the top of that curve comes out about the same. And this all relates back to that nitrogen use efficiency. So how do we create a recommendation from this? Now, that relative and standard yield only will take us so far, but if we want to really hone in on making the most profitable crop and also reducing potential nitrogen, we can start looking at the economic optimum nitrogen rate. So this is a table that's going to be available in all of NDSU's nitrogen recommendation printed catalogs. And essentially it's plotting barley price on one side, and then the cost of nitrogen fertilizer that you'd have to purchase on the other. So remember, 186 pounds of nitrogen per acre is where we'd reach that maximum potential yield using our standardized yield approach. But if we take some economic factors into consideration, let's say we have to pay $1 per pound of N just because it's nice and easy, and we're selling our barley for $6 per bushel, that would bring the economic optimum N rate down to 124 pounds of nitrogen per acre. Now that's a significant decrease in the amount of nitrogen we need to apply, which is kind of scary to think about. But also remember how close we were at that maximum nitrogen rate to being too high of a protein content. By applying less, that's going to bring our protein content down, where that way in the majority of years, we would meet that quality requirement. Now you might be asking, how can we apply that lower rate of nitrogen and still be profitable? Well, that comes in the tale of two nitrogen rates. So as a farmer, you don't believe that you can make the most amount of profit by applying that lower amount of nitrogen. So this essentially is showing at that same $6 per bushel barley, $1 per N of nitrogen, our fertilizer cost is going to linearly increase. Regardless of how much nitrogen we apply, pound for pound, it's always going to cost us the same. But this gross return you can also think of as that yield curve. As we get closer to that maximum potential yield, it takes more nitrogen per unit of yield increase. So at that 125 pounds economic optimum rate, we land perfectly on top of that net return. So fertilizer cost minus our gross return minus the fertilizer cost, giving us that net return. Now, if you wanted to fertilize to maximum yield to make sure we're at the top of this gross return, our net return is going to be lower. So that comes out to be, as it relates to return to nitrogen. So remember, this is all being measured right now in dollars per fertilizer. If you had to purchase this nitrogen, your return on that would be around $200 per acre applying that economic rate. Now, if you were shooting for maximum yield, your return would be around $173 per acre. So you would be making less money by growing more crop and also have then a higher dependence on fertilizer nitrogen. Now that rate does seem pretty high, but we have to remember we're measuring this in total known available nitrogen. So we take that recommended rate at 125, say we can subtract off 40 pounds of legume credits. Last year we had a soybean or a dry bean crop. And also we tested our soil nitrate prior to crop planting, and that showed we had 45 pounds of nitrogen in our soil. So that brings the amount of fertilizer we actually have to apply down to 40 pounds of N per acre. So that would be equivalent to, 100 pounds of urea, for example, we would have to apply. And recognizing that the fertilizer is, significantly less than what that rate is, that's going to drive up our return to nitrogen by almost 3 times. So now we're starting to talk about real numbers. So all of this stuff and all of these tables, how did we deliver these to farmers in a way that's easy to use? At NDSU and across the country, we've developed nitrogen calculators. So essentially for all the major crops here in North Dakota, corn, wheat, durum, in addition to the barley and sunflower, we have apps available for both Apple and Android, along with a web-based version, where farmers and practitioners can enter parameters on their field. So that regional productivity that I talked about earlier. We have research that shows your tillage system actually has a bearing on the way those nutrients cycle, in addition to that previous crop credit, residual nitrate, and then those economic factors. And that will just give you what our research shows is going to be the optimum nitrogen rate for you to apply. We also release this information in extension circulars. So that QR code that's up on the screen now will link you to fertilizing, malting, and feed barley extension circular that'll include a lot more information on what I talked about here today. And I'm also happy to announce as of last week, our paper in Agronomy Journal has been accepted and will be published, managing nitrogen to promote quality and profitability of North Dakota 2-row malting barley. And this paper we wrote really digs into some of the equations and the mathematical basis for why these recommendations work and why they should be extended to other states, not only to increase profitability, but also to reduce our dependence on fertilizer nitrogen, making sure that we're using it as effectively as possible, which in the long run is going to improve our environment as a whole. So with that, I am at 25 minutes. I will turn it back over to the moderator.
Great. Thank you very much, Brady. So hopefully you can see why we wanted Brady to present today, because as we talk later this afternoon about lowering greenhouse gas emissions, thinking very intently about carbon in our systems, we all know that nitrogen is going to be one of the areas we need to focus on and make changes if we're ever going to start moving the needle. And the amount of thoughtful work that went into this research to really hone in on what those recommendations should be, I think is going to be a part of that equation. So I'm really excited to share Brady's work and hopeful that we can be able to extrapolate this across other states as well. And so with that, we do have time maybe for a couple questions. Does anyone have a question for Brady? Yeah, Brianna. Or Sarah, sorry.
Have you done any similar PK or S?
So the question was, Brady, have you done any other similar work for PK or S?
So there is economic recommendations for potassium here in North Dakota. We have not done that for phosphorus. There's currently somebody that's working on a project looking at that in soybeans. We haven't done that in malting barley. And sulfur also, the rate that we have to apply sulfur is quite a bit less than we do the other nutrients. So the economic bearing on that isn't necessarily as strong. And then also the environmental implications of sulfur are a lot less impactful than the other nutrients. We certainly could do it for all nutrients, but the usefulness of some of that gets a little bit shady. But there is that for our potassium recommendations.
Is there another question? Yeah, Rich Horsley.
Yeah, if you take into consideration on your nitrogen rates, protein level, make sure that you're keeping the protein level below 13%. For an adjunct factor 11%.
Yeah, Rich's question just was related to protein levels. Just whether or not he was keeping track of those on that curve.
Yes, we were. So earlier in the presentation, I showed that kind of yield curve would max us out at that about 186 pounds of nitrogen. When we relate that back to the protein content, that would land us at a protein of around 12.8% if we were shooting for that maximum productivity. When we start honing it in a little bit for the economic rates, we were always below that cutoff for protein.
Any other questions? Yes, Mitchell. Yeah, so Mitchell's question was related to varieties and whether or not those are incorporated into those recommendations.
Yes, so we used 2 different varieties to create these recommendations, and we did see differences in the way that these varieties reacted to nitrogen. In some of my background analysis, I split these out and just hypothetically did nutrient recommendations independently for each of these varieties. There were differences, but not enough that could justify us doing recommendations for every single variety.
Great. All right, well, thank you very much, Brady.
Yeah, absolutely. Thanks for having me.